Yeah, it is. That's okay. We'll talk about good stuff. So, most important thing first. I briefly had the high score, but I was soundly knocked out of first place by.
I got knocked out of third. No. Wait, somebody got 7,500?
Yes, level 19, killed by a griffin. So.
That's actually super close.
Yeah.
What is level? It's like below level 20 is where the end of the game is.
Supposedly, I think it's 31.
Is it?
Yeah, that's what I heard, but that was a long time ago. And your goal is to get the Amulet of Yendor and then come back up through the dungeon and escape.
Oh, we have to come back up.
Yeah. That's why you can't go up the stairs normally, because you need the amulet.
But it would be increasingly easier as you ascend, right?
Yeah, and I don't know if it preserves the maps on the way up. But if not, you could write down where the stairs are on the way, and then you could, like, hopefully get there more quickly.
Shortest, yeah.
But, yeah, so.
Bring back to your.
Oh, but you're gonna run out of food. Because you, if you spend the early levels gathering food, then you're gonna run out of food on your way back up.
Yeah.
You gotta be careful about that.
Yeah, I ran out of space just getting to level 17. I had to keep dropping stuff. So yeah, the bar has been raised significantly.
Wow.
Yeah.
Yeah. That's a long ways down.
Yeah.
The deepest I got was like, what, 14 or something?
If you read the backstory for the game, you have to bring it back so you can get into the guild.
Nice.
That's like your quest that they send you on in order for it to join.
That I didn't know.
It's a hard quest.
Right?
What kind of guild is this? Have they all done this?
It's the 222 guild. So I posted a study guide for the midterm. I'll probably go over this tomorrow, because otherwise I'll have to go over it tomorrow anyway, because lots of people aren't here. But there's no big secrets in here, other than make sure that you know how to insert and remove things from a queue. Okay, I'm going to have a question about that on there. So make sure you know you insert at the tail and you remove from the head, and what that looks like. So there's the head and the tail, and if you insert a 15, that goes over there. And if you insert a 20, right, that goes at the tail. And if you insert a 7, then you could draw it like this. Right, so they keep going up that way. When you remove, you would remove the 15 first, and that comes out of your queue. Right, so things are basically going in tail side, coming out the head side. Right, a stack, if this is where the top of the stack is, if you push a 15, that goes on the top of the stack. If you push a 20, that becomes the top of the stack. The 15 goes down. If you push a 7, that becomes the top of the stack. The 20 goes down, the 15 goes down. So you're putting things in on this left side, and then when you say pop, you take them out from that same side also.
So you're working with a queue, and you encounter something that can't be resolved immediately. Is there ever a case where you'll skip an item in a queue and then do the item below it and then return to the previous item?
Like processing jobs or something?
Yeah.
Yeah, typically not in a pure queue, but sure, you can definitely have things like that. In practice, you know, you could remove from the head and put it back in the tail, but if you wanted to just kind of peek ahead and grab something that's like 2 spots in, I mean, you could write functions to do that. And that gets a little bit into the motivation of a priority queue, where you might have multiple queues and you grab from the front of whichever queue has the highest priority and has something ready to go. All right, so we can go through this in detail tomorrow, but you can look it over and bring questions if you have them. But basically, it's going to be everything we've been doing up through linked lists, hashes, stacks, and queues. I won't ask you to code stacks and queues, but I may ask you questions about them. Okay. Good question. Friday.
This Friday?
Yeah. I know, we're like in week 5. We're like,
Weird, I always see posts what people do is like the longest month ever.
week 5. Yeah, I believe so. So
Yeah.
Friday's like the halfway point of the course.
Oh, way.
Yeah, it's really weird.
What? It's just because we haven't had any snow. That's why it's.
That's
going
why
by
it's
so fast.
weird, yeah, must be.
The make files, if we just gonna test this on like the make files and the program standards.
Yeah, so what's the purpose of a make file? What does a make file typically look like? Or here's a make file, if you do such and such, what will happen when you say make? Stuff like that, but nothing too sophisticated. I feel like we should be sitting in a circle or something.
You know, the outside classroom.
Yeah, we could have outside class, that would be perfect. Yeah.
Snowball fight?
Yeah. Yeah, we could like do a linked list snowball fight.
We can queue up some snowballs.
Yeah, yeah.
Maybe
What's
cues
that
as well.
like? What's that?
All right, well, we were talking about trees. And let me just throw out a little bit of code, but we're mostly going to work abstract for a while, but just so it's out there. What does a node look like for a tree of whatevers, say integers? Right, so you need some sort of data piece. And then, just like a linked list, you need a pointer to the node on the left, and you need a pointer to the node on the right. And that's pretty much it. So, very much like a linked list, but 2 pointers instead of 1. And in general, we're not going to have sentinel nodes for trees. Okay, so forget about sentinel nodes for the most part. And we'll deal with the complexities of, for example, if you have an empty tree, the root is null. If you insert something, then your root is not null. It's whatever happens to be the root node. And so we'll have some edge cases in our code, but it's not a big deal. All right, so we'll write code later, but let's keep looking at these things kind of abstractly. And we're going to stick with binary search trees. So binary search tree, everything on the left of a node is smaller, everything on the right is bigger. So we could have something like this. And unless I messed up, that's a valid binary search tree. And it's not always going to look like a nice, fully symmetric, fluffy tree. Right here we've got, some branches coming off here to the right, and this is nice and balanced, but it's all kind of hanging off to the left. And there's a notion of when a tree is nice and symmetric and fluffy looking, right? It's called balanced. And balanced trees get you higher performance. And after we go through everything there is to know about trees and we talk about some code and we get into PA4, we'll start talking about balanced trees. And it's a kind of whole separate topic of how we try to make a tree look nice and balanced. But consider this. Is that a valid binary search tree? Yeah, absolutely. Right? No root has more than 2 children. No node has more than 2 children. Everything to the left of a node is smaller than everything to the right. That's a binary search tree. But it's also just a linked list, right?
Yeah.
We're not using the right pointers. We can start from here and we can follow to each. So if we try to search this tree, for example, we get order n performance, right? But technically it's still a binary search tree. But we could also we could make this so it was shorter and wider and get better behavior. All right, so let's look at this tree. So suppose we want to search for something in this tree. Suppose we want to search for the number 28. Remember, we're playing high-low, right? But we've got our array drawn differently. We always start from the root. And if that's the number we're looking for, we're done. If it's not, if the number we're looking for is bigger than the root, then if the number is in the tree, it must be somewhere in that right subtree. Because everything to the left of the root is smaller than the root. So if we're looking for something bigger than 100, it can't be in the left subtree. It's got to be over here. In this case, 28 is smaller than the root. So if it's in the tree, it's got to be in this subtree over here. We can completely ignore this right subtree. And again, we compare 28 to the root, and it's smaller than 50. We can ignore all of this, and we can say, okay, if it's in our tree, it's got to be over here. 28 versus 25, 28 is bigger, so we're going to ignore if there was anything to the left of 25, and we're just going to search this subtree. And we check, is 28 equal to the root? Hey, it is. We found our number. If we were looking for 29, we would have done the same thing until we got here. 29 is bigger than 28. We'd say, okay, we have to check the right subtree, so we check this subtree, which is null. At that point, we know 29 is not in the tree. So our searches are going to be really efficient. The time it takes to search is going to correspond roughly to the height of the tree, the number of steps from the root to any particular node. And what's the height of the tree look like for n nodes? So there's 15 nodes. And what's the height of this tree? You say it? I don't know. Is it 4 or 3? 3. It's one of those, yeah. So from the root to any node, 1, 2, 3 steps. And if I were to add another 16 nodes, right, I could hang another pair of nodes off of each of these, and the height of that tree is 4, and I've doubled the number of pieces of data in my tree. So twice as much data, and my search time has increased by 1 operation. Right? That's what an order log n feels like. You double the amount of data, and your time to perform your operation goes up by a fixed amount, in this case 1 operation, 1 extra search. So search is going to be order log n, which is a really nice order of complexity. But that's assuming that these 31 pieces of data are in this nice fluffy tree. If they actually looked like this. Right, my search time is going to be order n. So searching will be nice, and the way we search fairly straightforward. So let's say search t comma n. So we're searching for a number n in this tree t. So if t's root is equal to n, we can return right there and say we found our number. If our number is bigger than the root, we can set t equal to its right child. And we can just go back up here. If n is less than t dot root, which is the only possibility, because if it's equal, we've returned. If it's greater, we've already gone back up to the top. So if n is less than the root value, set t equal to the left child, and go back up to the top.
Basically, in high-low last column, we get the average.
Mm-hmm.
This case, not with it.
It's basically the same thing, yeah. Right, so we're guessing a number in the middle. That's what the root is. If that's the number you want, you're done. If your number is bigger than the number in the middle, we're basically saying, okay, let's just work on that right side of the array, right? The right subchild of the tree, and go back and repeat this process. And how do you know if the number's not in the tree? What's going to happen eventually? Yeah, eventually t is going to be null. So if t is null, we can say it's not found. If the root matches our number, it's found. Otherwise, we break the problem into either the left or right subtree, and we repeat the steps. So that's a perfectly fine iterative search algorithm. Iterative meaning there's a loop, right? We keep going back up to the top, so we've got a while loop or something. And we just do these operations. There's another way we can do this, though. If we go back to our original tree, and let's think lazy again. Someone hands you this tree and says, I want to know if the number 28 is in here. And you don't really want to do a whole lot of work and loop and search all these subtrees and so on and so forth. So here's what you can do. Go ahead and compare 28 to the root. That's easy. If that's the number you're looking for, you can say, hey, I found your number and you're a hero, right? If 28's not the root, you can say, okay, is 28 smaller or bigger than this? It's smaller than this. So if 28 is found, it's got to be in this smaller tree. At that point, you say, I'm tired, I've done enough work. You find a friend, you give them this smaller tree and say, hey, can you tell me if 28 is in this tree? And they'll somehow figure out whether it's in there or not, and whatever they tell you, that's your answer for is 28 in this original tree. And you give that answer to your client. And your friend, who's equally lazy, does exactly the same thing. They say, well, let's see, is this 28? No. Is 28 smaller than that? Yeah. So they take this smaller tree, and they hand that to another friend and say, tell me if 28's in here. And each person is doing a very little bit of work. They're checking to see if the root matches the number. If it does, they say yes. If it doesn't, they take either the left or right subtree and they hand it to a friend and say, can you search this for me? And this goes on until you get to a friend who's been given, say, a tree that looks like this, and then asked, does this contain the number 28? And they look at the root and they say, yeah, it does. And that answer trickles back up. Or you were looking for 29, and somebody gets this tree with a single node, and you say, is this contain the number 29? And they say, well, let's see, the root doesn't match 29, so it would be in the right subtree. Oh, there's nothing on the right. Nope, 29's not in this tree. And that no answer circulates all the way back up. Right, so this is recursion. And the friend who is doing this checking for us is really ourselves. Right, we're just kind of like suspending where we are, and we put on a different hat. We say, I'm Nick's friend, and we work on this subtree. And as long as you have enough multiple personalities, you can keep doing this, and then you put on your other hats, and eventually you come back to Nick, and Nick's like, oh, my friend says the number's not in there. Guess it's not in the list, in the tree. And so if you want to do a recursive version of search, it looks something like this. So searching a tree for the number n. Well, if t is null, it's not found. If the root data is equal to it should be t dot data. If the root data is equal to n, it is found. If n is bigger than the root data, we return search t dot right, comma n. Otherwise, search the left subtree. And there you go, 4 lines of code. And I did this slightly differently from my example here. When you're given a node that's just a tree that's just a single node, you still go ahead and you pass your left or right subtree to your friend, and it's your friend who actually says, hey, there's nothing in this tree. I guess that number's not found. So 4 lines of code. Not found if the tree's got nothing in it, found if the root matches your number. Otherwise, I call the search function on either the left or the right subtree, and whatever that search call returns, that's what I return. And this really works. And once you start writing this stuff, it will feel like you are cheating. Right? It will feel like you're not actually doing any work, but you really are.
So we don't get the T arrow that
This is still pseudocode. Yeah. So if t is a pointer to a node, then you need t arrow. Yeah. And, you know, not found would be like a 0, found would be a 1, something like that. So this is a recursive version of this. This is an iterative version. Right? This never calls search, it just loops inside. And the looping's not all that bad to do. But some of the other things that we're going to do, like traversing a tree, which we're going to do next, the iterative version is fairly nasty. Because searching, we start at the root, and we just go root, boink, 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 boink. We just march our way down. And we never have to go back and do anything else. Right? Traversing a tree is going to be more like running a maze. We're going to have to remember at this point that we went left, but eventually we're going to have to come back here and go right. And when we come down here, we're going to go to the left and look at the 25, but eventually we're going to have to remember that we came from the left and we're going to have to go back to the right. We're going to have to keep track of all these points where we make a decision, and that's going to be where we use a stack to sort of remember all these decision points. So the iterative version of traversal is going to be kind of ugly. So let's talk about recursive traversal first. And remember, traversal means going through your data structure in some systematic way so that you visit each node. In this case, we're going to print each node that we visit. So our goal is, if we have a tree like this, we'd like to print out each number in this tree, and we want to print them in order. This is a binary search tree. Everything on the left is smaller, right is larger. If we traverse this, if we visit the nodes in the proper way, we'll visit them in increasing numeric order. And there's three ways to traverse a tree. We're going to talk about a way called LNR, which is called in order. And the definition is recursive. So how do we traverse a tree T in left node right order? You made it awesome. So there's three things we do. One, traverse the left subtree. Two, print the root node's data. And three, traverse the right subtree. So it's a highly recursive definition. So here's our tree. How do we traverse it? Well, first we're going to traverse this, and then we're going to print a 20, and then we're going to traverse that. Okay, how do we traverse this tree? Well, first we're going to traverse this tree, and then we're going to print the data at the root, and then we're going to traverse that tree. Okay, well, how do we traverse this tree? We're going to have to traverse its left subtree, which is null. And if I try to do that, I'm going to try to find the left subtree of a null root, and that's going to be an error. So we really need an extra statement in here, which is if t is null, just return. Okay, so we're traversing this subtree 5. So traverse the left subtree, well, that means we're going to have to traverse this null. And when we try to traverse that, it's going to say it's null, I'm not going to do anything. So that traversal has no impact. We're going to print the data at the root of this tree, so that's going to give us a 5. And then we're going to traverse the right subtree, which is also null. And when we call traverse on null, it'll just return. And we're done. So we've traversed this blue tree, and we got a 5. And remember, we were traversing this 3-node tree. It wasn't null, so our first step was to traverse the left subtree, which is a 5. We've already done that. Now we're going to print out the data at the root of this tree. So that prints a 10. And our last step is to traverse the right subtree, which is this blue 15. So we're going to traverse the blue 15, and that says traverse the left, which is null. And when we traverse that, it'll just return, and then print the root data, which is 15. So we'll print that. And then traverse the right subtree, which is null, and when we call traverse on null, it'll return right away. And then we're done with the traversal of this blue 15 tree. And that was the third and final step of traversing this 3-node tree. So traversing this tree gave us this output. And why were we traversing this tree? Because we were traversing this original tree, and the first step was to traverse the left subtree. So we just finished step 1 of our original traversal, and now we print out the root node data, which is 20. And we only got one more thing to do, which is traverse the right subtree, which is all of this. And you can see what's going to happen. We're going to go back down the rabbit hole, and to traverse this, we're going to have to traverse the 30, and that's going to have nothing on the left, and we're going to print the 30, nothing on the right, and that'll complete step 1 of traversing this. Step 2 will be to print the root data, and step 3 will be to traverse the right subtree, which will print a 60. So trying to keep track of what this is doing can drive you nuts, especially if your tree is really big. But at some point you won't have to keep track of it like that. You'll be able to think of it in terms of this algorithm itself. So traversal is a 4-step algorithm. If the tree is null, just return, otherwise traverse the left subtree, print the root data, traverse the right subtree, and you're done. And the computer keeps track of all of this, keeps its finger here and says, okay, now I'm doing this, keeps a finger here, says I'm doing this, keeps a finger there, looks to the left, prints the root, comes to the right, comes back, and so on and so forth. Does that make some sense? Does it seem bizarre at all? Mixed responses, good. It always seems a little bizarre to me. So here's a different way to think about this. So we want to traverse this tree. So to do that, we have to do 3 steps. Traverse this tree, print a 20, and then traverse the right subtree. All right, so those are the 3 things that are going to happen inside our call to traverse. But this is going to require a number of steps. It's going to need to traverse a tree containing a 5. It's going to need to print the root node, and then it's going to need to traverse a tree containing just a 15. And similarly, this is going to say traverse a tree containing a 30, print a 40, and then traverse that last subtree containing a 60. And traversing a 5 says traverse null, print 5, and traverse null, and same thing. And you get the idea, right? So what's actually going to happen, we call traverse with this tree. That creates a call to traverse with this tree, which creates a call to traverse with this tree, which creates a call to traverse with null. And then prints a 5, and then calls traverse with null. And then returns to this call to traverse, which next does a print, and then calls traverse 15, which calls traverse null, prints 15, calls traverse null. Returns to here, which returns to here, which goes on and then prints a 20, and so on. So how does this work? The computer's keeping track of all of this for you. Right? Just like when you call a function, it has to remember where you made that call from so you can return to the next line after the call. And it does that by pushing that return address on the stack. And similarly, when you call a function, if you have local variables in there, if you declare integer I equals 12, it's got to somehow remember this local variable I is equal to 12. But if you had a variable I in your program that made that call, it's got to remember what that value of I was. So that when you return, that value of I is whatever it was before. Right? So the calls don't affect local variables outside of their own context. And that's also done by using the stack. When you have local variables in a program in C, those variables are stored on the stack. And when you return, all that stack space gets reused, but the stuff that was present before the call is still there, unchanged.
So does that mean separate instances of the same function, even though it's the exact same function, each have their own individual local variables?
Absolutely, and that's the only thing that allows you to do this kind of recursion. So here's a function. So you have a function and it's got a local variable I, and at some point it calls itself. When you call this function, if inside this call you change the value of I, when you return, the value of I is back to whatever it was before you made this call, even though it's the same I. Right? So local variables are always kind of part of the call frame, the context of each function call. And same function name, same variable name, doesn't matter. It's purely local. When you come back, any local variables in here are back to what they were before you called. All right, that's one of the benefits of pass by value also. And so this is why we can do things like a recursive factorial function. So factorial takes an argument n. If n is equal to 1, we just return 1. Otherwise, we return n times factorial n minus 1. And that's recursive. And n is a local variable, right? It's the argument to the function. But when I call factorial, if I call factorial 5, from my main program, when I first come into fact, n's equal to 5, down here I'm going to call fact 4, then that new instance of fact, n is equal to 4. When I return, n will be back to being 5, and I'll multiply 5 by whatever I got from fact 4. So this is something we can call tail recursion. The recursive call happens at the very end of our function. And tail recursion we can replace with just a loop. This is recursive throughout the function. We recurse up here and we recurse down here. And it's harder to replace with a loop. But we can do it. So let me show you what that looks like, just as another motivation for a stack. So traverse.
Sorry, it's time to wake up.
Yeah, I like that. So let's traverse a tree using a stack. So 5 steps. Step 1, push the root. Let's say t.data. Okay, step 2, if t dot left is not null, push t dot left, and go back to step 2. Step 3, pop, print, and if stack was empty, then you're done. Alright, if t right is not null, push it onto the stack and go to step 2. And step 5, go to step 3. And this should actually be t equals pop. Alright, there's a 15% chance that I've made a mistake here. So traversing a tree T, so push the yeah, it's a pseudocode. I'm not going to get too bogged down on what data and left and right are. So push the root node of the tree right onto the stack, and then if there's something to the left, push that. Go back to step 2. If there's something to the left, push that. So keep pushing left nodes onto the stack until there's nothing to the left. And then do a pop, print that out, and then if there's something to the right, push that and go back to step 2. Otherwise, go back to step 3. So let's see if this actually works. So we'll make a stack. We'll grow the stack in this direction. And so here's our tree T. Okay, so first thing we should do is push the root node onto the stack. So we push a 40. And then if there's something to the left of T, we want to push that left node. So we'll push a 20. Let's see. So if there's something to the left, we're going to push that node onto the stack, and that's going to become our new node T. And we'll go back to step 2. So now we're sitting at the 20, that's T. If there's something to the left, we're going to push that left node onto the stack, and we're going to change T to be that left node. So now T is this 10. If there's something to the left, we will continue, but there's nothing to the left, so we go on to step 3. So we pop off the top of the stack, which removes this 10, and we print that out. So here's our output. So we print out a 10. And then if there's something to the right of that, we would push that, but there's nothing to the right. So we're going to go back to 3, which says pop top of the stack. So we pop off the 20, and we print that. And now this is T, and if there's something to the right, we're going to push that onto the stack. So we're going to push a 30, and T will be this node here, and we'll go back to step 2. If there's something to the left, nope. So pop off the 30, print it. And then if there's something to the right, nope. So we go back to step 3, which says pop, so we pop off the 40, and we print it, and this is where T is. And now if there's something to the right, which there is, we're going to push that. So we push a 60, and we go back to step 2, and if there's something to the left, we push that, so we push a 50. We go back to step 2, there's nothing to the left, so we pop, there's our 50. And if there's something to the right, nope, there's nothing to the right of 50, so we go back to step 3, we pop, there's our 60. If there's something to the right, we push it, so we push our 70 onto the stack, and we go back to step 2, there's nothing to the left, we pop off the 70, there's nothing to the right, so we can't do step 4, so we go back to step 3, which says pop, our stack is empty because we pop the 70, we're done. So if we use a stack ourselves, we can traverse this tree, but we need the stack to keep track of where we are. So that each time that we move down, for example, to the left, we push our current location onto the stack so that eventually, when the time is right, we come back to where we were, we print the root, and then we move down to the right and repeat this traversal of that subtree. And this, to me at least, is really confusing. And this is, to me, very much how I think of recursion. How I think of traversing, right? Traverse the left subtree, print the root, traverse the right subtree. That's the definition of left node, right traversal. So this is left subtree, node, root node, and then right subtree. So we're not going to worry about this too much because we're going to move to where we're just doing recursion pretty quickly. So 2 other ways to do tree traversal. This is in order. We can do NLR, which we call pre-order. Or we can do LRN, which we call post-order. And it's named after where we print the root data. If we print it in the middle of the left and the right, that's in order. If we print the root data before going down left and right, that's pre-order. If we print the root after doing both the left and right subtrees, that's post-order. And you get different output in general depending on the order that you're using. But the code for doing these traversals is exactly the same. The only difference is when you do your print. If I move this up here, I've got a pre-order traversal. If I move this down here, I've got a post-order traversal. But exactly the same steps, just different order. And if I were to traverse right and then the root data and then left, that would be like RNL, where you're traversing the right subtree first. And guess what? If you do that, you get your numbers out in decreasing order. If you do post-order, and you make this tree that we had corresponding to expressions. If you do post-order, you get postfix, RPN. All right, so that's a bunch of material for 50 minutes. But we'll go over all of this again, and we'll start putting some code with it. So we need to talk about recursive search, recursive traversal, recursive insertion, and eventually we'll talk about deletion, but deletion is a separate can of worms. All right, so I will see you tomorrow. Stay safe.